MCQ 13 is going to be with regards to reaction kinetics, particularly with regards to half-life. So we're going to have a peroxide solution decomposing to give us water and oxygen. So we started off with the volume of the peroxide solution at 200 cm cube itself. So we can put 200 cm cube here. And after 120 minutes, this is the duration of the experiment, 6 dm cube of oxygen was collected at RTP. So that's going to be 24 dm cube per mole of gases. And the condition over here to understand is that we are having a reaction with a constant half-life of 40 minutes. So this statement here, in order for us to have a constant half-life, I mean, we can either take a look at the slow step, which is not given in this equation, we can determine experimentally, or it is with the assumption that the overall order of reaction is actually equals to 1. Now you can also see that we only have one reactant as well. If there's only one reactant and the overall order of reaction is actually equals to 1, that tells us that the order of reaction with respect to hydrogen peroxide is 1 as well. So indeed, we do have a constant half-life over here. Now we're going to go back and find out the initial concentration of hydrogen peroxide solution. So what I'm going to do here first is I'm going to let X be the number of mole of hydrogen peroxide at time equals to 0. That means the experiment has not started at all. So number of mole of peroxide as well as number of mole of oxygen. So this is at time is equals to 0. So the mole here is going to be X for the case of peroxide. So it's going to be 0 for O2 because it's a product. So again, at 120 minutes, and also knowing that it has a constant half-life of 40 minutes, that means we're looking at 3 sets of half-life. So I'm going to put 40th minute, we're going to have another 40th minute, and we're going to have another 40 minutes as well. So it's quite straightforward that for peroxide, when it half, it becomes X over 2. So the trick is really on the case of filling up for oxygen. So maybe just a small simple ice table will do the trick over here. So 2H2O2 becoming 2H2O plus oxygen in terms of mole. Again, if you could see this quickly, is unnecessary for the ice table. But if we're going to start off with X mole, and I know I'm going to half minus X over 2, based off the ratio of 2 is to 1. Alright, it should be actually a plus X over 4 because I need to divide the mole change by 2 because ratio is 2 to 1. So what I will get for my oxygen at the first half-life is X over 4, but what's left behind for my peroxide is X over 2. So over here I have an X over 4. Just remember, whatever change of peroxide, you can't have a direct change to O2 because the ratio of 2 is to 1. You have to divide by 2. So if I halve my H2O2 again, I'll get an X over 4. But this time around, it will be an X over 4 for O2 plus an X over 8 for O2. This is based off the second half-life. I'm going to halve it again to give me an X over 8. So we're going to have the expression of X over 4 plus X over 8. But this time around, plus another X over 16. So in the final mole portion over here, the number of mole of O2 at least final at 120 minutes, it will be the sum of this X over 4 plus X over 8 plus X over 16. That will give us a 7X over 16 mole. Now we do know that the volume itself produced was 6 dm cube, and this is at RTP. So 7X over 16, which is the volume of O2 final at 120 minutes. We'll multiply this by 24. We know that this will be equals to the value of 6. So solving up for the value of X over here, we get an expression of 6 times 16 divided by 24 divided by 7. It will be 0.57143. Alright, this is the number of mole of peroxide that's at the start. So in conclusion, if you wanted the concentration of peroxide, we'll take the mole that's at the start at 0.57143 divided by the volume of peroxide of 200 cm cube divided by 1000. That will get us the value of 2.85. And since all, if not most of the answers, there's a 2 dp answer here, but this is out already. Alright, so most of the answers are in 1 dp. For the remaining, if I round it to 1 dp, this will be 2.9 moles per dm cube. So the answer here is